Hello method students, and welcome back to another video. In this video we're going to go through some example of differentiating circular functions. You might have already had a look at a sort of general video that explains why sine x and cos x have the derivatives that they do. If you haven't already seen it, it might be worth a look, but let's get stuck into some examples where we apply those rules to some different expressions. So in general, let's just sort of start from the start. We say that if y equals sine x, then dy dx is cos x, so the derivative of sine x is cos x. But as we've seen in other functions, when you have more complex expressions, you can use the chain rule to differentiate them. So we can extend it to say that in general, if y is equal to m sine of f of x, then dy dx will be equal to m, so the constant stays in front, times f dash of x, which is the derivative of the bracket, which is really how we're applying the chain rule, times cos of what was in the original bracket, right? So you can kind of see that the sine of bracket has become cos of bracket, but we've also multiplied by the derivative of the bracket, which is the, well, I didn't explain that all that well, but that is the chain rule. So in example 18, we're told that if y is equal to sine of 5x, we have to find dy dx. Now, as we've done with a couple of other videos, let's just kind of do it the slow way first, if you like, and say we'll let u equal 5x, right? Remember that this method is, you know, the long way of doing the chain rule. Can be handy if you want to kind of see why it turns out the way it does when you apply the shortcut method, or it could be useful for, you know, if you had a really complicated expression in here and it's hard to see what your answer is going to be. This can be a good method to fall back on. So if u equals 5x, then du dx would just equal 5, but also that would make our original expression become y equals sine of u, and that means that dy du, derivative of sine of something, is cos of something. We've just established that. So because u, and then when you bring the two parts back together and say dy dx equals dy du, which is 5, times du dx, which is cos of u, you can see that you're just going to get 5 cos of, and when we undo the substitution, u becomes 5x. So our derivative is 5 cos of 5x. Now, the much easier and quicker way of thinking of that is to just say, okay, well, from my original expression, all I'm really doing, differentiating inside the bracket, derivative of 5x is 5, times differentiating the outside function, so sine of something becomes cos of that thing, so it's 5 times cos of 5x. And because we're year 12 method students, we can write that without the time symbol. Right, so clearly shortcut way much quicker. All right, let's have a look at another one, and we'll just go straight to the shortcut method. So the derivative of 5 sine of root x, we might want to write that as the derivative with respect to x of 5 sine of x to the power of a half, or at least think of it that way, because that's going to be easier to deal with the derivative. So the derivative of 5 sine of x to the power of a half, well, I'm going to firstly, well, let's stick with the same structure as this rule above, actually. Let's keep the constant there first. So the 5 stays in front. I'm going to multiply by the derivative of the bracket, which is a half x to the power of a negative a half, so just multiply by the power, subtract 1 from the power. And then the derivative of sine of something is cos of that thing. So cos of x to the power of a half, and then we just tidy it up a little bit. So let's see, we've got 5 and cos of root x on top. So I'm just going to rewrite x to the power of a half as root x again. And the bits that are going to end up on the bottom of this fraction would be the 2 from that half, and also x to the power of a half comes down to the bottom as x to the power of negative a half comes down to the bottom as x to the power of positive a half. So we'd get a 2 root x on the bottom there. Okay, moving on to derivatives of cos x. So the derivative of cos of x is equal to negative sine x. And again, extending that to apply the chain rule for more complex expressions. If y equals m times cos f of x, then the derivative is going to equal negative m, so constant stays in front, times by f dash of x, so the derivative of the bracket appears here as well, times sine of the angle that we had, or the whatever we had inside the bracket originally. You can kind of see where the negatives come from is that the derivative of cos f of x is going to be negative sine f of x. And so, yeah, I guess quite similar to what we did when we're differentiating sine. We just have to be aware that our expression is going to become negative when we're differentiating cos. All right, so let's have a look. We've got, find the derivative of cos of x squared minus 1. First thing we can think of is, okay, well, what's the derivative inside the bracket there? Derivative of x squared minus 1 is 2x times by the derivative of cos of something is negative sine of that thing, right? What's in the bracket doesn't change. That's kind of been consistent throughout every time I've used the chain rule. And then we can just tidy that up a little bit and say that it's negative 2x sine. Oops, don't know why I gave that a plus. That should be a minus. Negative 2x sine of x squared minus 1. Alrighty. We've done sine, we've done cos. You guessed it, we're going to differentiate tan now. The derivative of tan x is probably one you're going to get asked about a little bit less than the other two, but the derivative of tan x is 1 over cos squared x. And 1 over cos x actually has its own function. It gets its own name, so that the function 1 over cos x is actually called sec, or it stands for the secant, sec of x. You don't really need to know much about the function sec of x in methods, other than you have to pronounce it very carefully. But it's just important for us to know that the derivative of tan x is 1 on cos squared x or sec squared x. Now, you'll probably use the 1 on cos squared x a bit more because we're familiar with, you know, calculating exact values of cos x and stuff like that, whereas we haven't really learned much about sec x at all, and we don't need to. But either of these two things can be used in your answers, and they both mean the same thing. Okay, so not super important for us to know, you know, graphs or solve complex equations involving this thing, but that's just a useful fact to have in the back of your mind, or in your summary book somewhere, more importantly. Okay, so example 20. Determine f dash of x given that f of x equals 2 tan of 3x plus 1. All right, so we know that if we're going to apply the chain rule, well, we have to have the derivative of the bracket in there, and the derivative of 3x plus 1 is going to be 3. The constant that was in front stays there, so we've got to have a times 2 at the front still. And we just said before that tan of x, or tan of something, differentiates to sec squared of that thing. So sec squared of 3x plus 1. All right, you can, you know, tie that up a little bit and just say that's 6 sec squared of, oops, making lots of mistakes in this video, 3x plus 1. And that's perfectly fine to give as your answer. In fact, it's probably easier to write that as your answer. Or a perfectly legitimate way of expressing it is to use 1 over cos squared x, 1 over cos squared x instead of sec squared x. So you can also say that it's 6 times 1 over cos squared of 3x plus 1, which of course is just 6 over cos squared of 3x plus 1. As I said, either of those answers are completely fine. I would probably say if all you have to do is write down f dash of x, that's just slightly easier to write. If it was a question that was asking you to, say, sub in an x value and do some calculations, so you had to work out your exact values, well, you'd use this one because you know how to work out things like cos of pi on 4, or, you know, cos of 2 pi, and so on and so on. So use this version if you have to substitute an x value in. Use this version if you just have to write down the derivative. That would be my tip. Okay, Lucky last example, this one says to find the gradient of y equals square root of 4 sine x at the point where x equals pi on 3. So this is a differentiate and then sub in. All right, so let's get stuck into it. Probably before we differentiate, there's a couple of things we can do here. We can split this original statement into square root of 4 times the square root of sine x. And it's useful to do that because obviously the square root of 4 is 2. And then we can also think of this as being sine of x to the power of a half. And so when we go to differentiate this, we can say, okay, well, what we're really doing, what we're differentiating here, the inside of the bracket, so to speak, or if we were to use the u, we'd be saying let u equal sine x. So the derivative of inside the bracket, derivative of sine x is cos x. Still got to have that constant out the front. And then differentiating the outside of this function, where we get a half sine x, and then subtract 1 from the power, we get negative a half. So that's kind of applying the chain rule using the shortcut method. As I said at the very start with the first example, if this one just felt complicated, you could always do it the so-called slow way and let u equal sine x, and then differentiate your two different parts separately. And then your job, whichever method you've used, is to sort of tidy it up a little bit. We've got, well, 2 times a half, that's convenient, that's going to cancel. We're going to have cos x over, now sine x to the power of negative a half can go to the bottom and become sine x to the power of positive a half, which is the square root of sine x. And remember, this question was saying at the point where x equals pi on 3. So that was dy dx. So when x equals pi on 3, dy dx will equal cos pi on 3 over the square root of sine pi on 3. So if you remember them, that's great. If they don't come back to you straight away off the top of your head, you can go to your triangle and draw the triangle that's got the angle pi on 3 in it, which is this angle down here. So there's pi on 3. So cos of pi on 3, adjacent over hypotenuse, cos of pi on 3 is a half. Sine of pi on 3, well, opposite over hypotenuse is root 3 on 2. So it's a half over the square root of root 3 on 2. Now that's a little bit messy looking, isn't it? Let's try to do some tidying up here. How could we say this? I'm going to run out of space, aren't I? Let's make it, firstly, a half, let's not have fractions within fractions, divided by the square root of root 3 on 2, which is, I'm going to try to do 2 things in one step here because I'm running out of space. We're going to tip and times, but I'm also going to work out the square root of root 3 over 2. Square root of a square root really gives us like the 4th root, and the square root of 2 obviously is 2, but I'm going to tip and times that in the same step, so I hope this is easy enough to follow. So we're going to have a root 2 on top, and then a square root of the square root of 3, which is the 4th root of 3 on the bottom. And when we combine these two fractions by multiplying, we're going to get root 2 over 2 times the 4th root of 3. It's probably a messier answer than you'd normally have to write down. I don't remember if I've just made this example up and mucked it up because I thought it would give you something more straightforward. But anyway, there is the gradient. Remember, coming back to the question, that is the gradient of y equals square root of 4 sine x at the point where x equals pi on 3. There's our gradient, and you try your best to make that clear that Mr. or Mrs. Examiner, that is my final answer down here. But you'd have more space in the exam anyway. All right, that's enough out of me. I hope that makes things a little bit easy to understand in terms of differentiating sine, cos, and tan. But as always, get in contact with your teacher if you're getting stuck on questions and you need some help. Enjoy.